EnerCalc 3D has a powerful fluid load generator, and what better place to take a look at fluid loads than a cylindrical tank? So, in order to understand how the fluid load generator works, the first thing we'll do is take a quick look at how shells are oriented in this tank. I'll use the option to hide all except for the XZ plane, which is where I've placed the bottom of my tank. And then I'll choose the option to display shell local axes. If I rotate this on edge, we can see that the blue local Z axes point upward on the bottom. Then I'll click Show All, and we'll rotate so that we look downward. And now we can see that for the walls, the blue local Z axes all point toward the center of the tank. So we have shells that point upward and inward. That'll come in handy for establishing the direction of our fluid load. And now I can turn off the display of the local axes. I'll use the keyboard shortcut Control A to select all of the shells in the model that I want to have load, which is all of them in this case. And then I'll come to Create and over to Load Cases just to show that I've already created a load case called Water, and we'll use that for our hydrostatic loads. We'll also assume that my goal is to fill the tank with water and to fill it all the way to the top. So on the Create tab, I can click Generate Loads and then choose Fluid Loads. The first option is the load case, and I do want this load to go into the load case named Water. The next option is very important. It defines the direction of variation of the load. So since this load varies along the height, which is parallel to the y-axis, we want to make sure that this item is set to y. Our load varies as we move along the vertical or the y-axis. Now we have a small table to fill in where we specify the magnitude and location of what we want to call the start, and likewise for the end. I want to think about the bottom of my tank as being the start, so my coordinate is 0 for the bottom. And I've already calculated that my magnitude will be 880 pounds per square foot. I know that the tank is 27.5 feet high, and I know that I want it to taper to atmospheric pressure, so therefore the hydrostatic pressure should taper to 0. Now, this is the key. Surface loads will be applied to the selected shells in their local Z directions. Remember that we started by taking a look at all of those blue local Z axis directions, and they pointed upward on the bottom and they pointed inward on the walls. That's exactly the opposite of the direction that a water pressure would push on all of these shells. So we just come into this magnitude and specify it as a negative value. This way our water pressure on the bottom should be pushing downward, and on the sides it should be pushing outward. Now I'll click Apply. We'll see a graphic of the generated loads, obviously a little bit difficult to interpret, so we'll come to Settings and Tools, and then change our graphic scale for area forces. Let's just see what happens if we bump this up to 600 pounds per square foot per foot of graph. And then let's make sure that we can still rotate this model. One thing that we can see is that we have 880 on the bottom, which is exactly what we would expect. And when we look at the direction arrows, we can see that that pressure definitely points downward, and so that's a good thing. We have a little bit of trouble interpreting some of the other data because there's just so much going on. So what we could do is we could come back to create and then use line select. And let's just draw a cutting line across one set of shells. Then let's go to invert that selection. Then I'll come over to the View tab and say Hide Selected. That greatly clarifies what we have left to look at on the screen. And now it's much easier to see that the load starts at some magnitude down here, 836 or thereabouts, and stepwise incrementally varies as we climb up the sides of the tank. Now, a couple of things to note here. First, the pressure is directed outward. That's definitely what we want for a hydrostatic pressure. The other thing is this little discrepancy that we see here between the 880 that acts at the bottom of the tank and the 836 that acts on the first ring of shells. That's because the program has found the midpoint of this first ring and done a linear interpolation from 880 to 0 and found that at the center of this ring of shells the pressure is about 836 psf. The same thing holds true at the top, where instead of tapering to 0, this shell has about 44 psf applied to it. The last thing that's important to know about fluid pressures is that we could come to tables, and then remembering that fluid pressures are defined as or created in the form of surface loads, we can use the surface loads table to review everything that's been applied to this model. So we can see the shell that has a received load, the direction and the coordinate axis system that were used to define the load, the magnitude of load that applies on that particular shell, and then if we scroll downward, we see the variation in pressures because we're actually working our way upward toward the top of the tank where the pressures are less. So this table is live, and if we wanted to make any edits to either the magnitudes or locations, we could do that, and those would be reflected in the model.